We are conducting a rigorous first principles breakdown of the BCS 501 Database Management System examination solutions, focusing on the mechanics that allow data systems to function under pressure. Mastering a DBMS requires proficiency in two specific domains. The first is relational schema design, which governs the logical layout. The second is operational state management, which governs the system's behavior during execution. These domains act as safeguards. Structural design prevents logical data anomalies from entering the schema, while state management prevents operational corruption when that data is accessed by multiple users or interrupted by failure. Our roadmap follows the progression of the exam. We will move through calculating functional dependencies, defining structural commands, proving the mathematics of lossless decomposition, and engineering ACID-compliant transaction locks. Solving these problems correctly demonstrates that a database can withstand the pressures of both structural scaling and catastrophic system crashes. Question 1A establishes the foundation of relational identification. A superkey is any set of one or more attributes that, taken collectively, allow us to uniquely identify a specific tuple in a relation. A candidate key is more specific. It is a minimal superkey, meaning it contains the smallest number of attributes possible to maintain that unique identification. If you remove any attribute from it, it loses its status as a key. We use question 1D's dataset to verify dependencies. Testing x to z. When x is 1, z is 2. This holds true. Testing the reverse, z to x, fails. When z is 2, x is 1 and 3. Multiple outputs are mathematically invalid. We find the candidate key using closures. Attributes missing from the right-hand dependencies, A and B, must form the key. Calculating their closure, A and B yield C, B yields E, and C derives D. Yielding all attributes proves A and B is the sole key. The final solution requires categorization. A and B are the prime attributes because they form the key, while C, D, and E are non-prime. These mathematical proofs ensure that a database architect can identify and eliminate hidden redundancies before they manifest as data corruption. Moving from design to implementation, question 1B contrasts the commands used to clear data, truncate and delete. Truncate is a data definition language, or DDL, command. It operates on the table structure itself. Truncate removes all rows by deallocating the data pages. It bypasses the transaction log and cannot use a where clause, clearing the table instantly without a rollback path. Delete is a data manipulation language, or DML command. It modifies the state of the data itself rather than the rigid structure of the container. Delete removes records row by row and logs each individual action. This allows for specific filtering and ensures that the operation can be reversed if the transaction fails. Question 1C introduces triggers, which are automated procedures the DBMS executes in response to these DML events. We distinguish between two types. Before triggers execute prior to the data modification to handle validation, while after triggers execute once the event is complete, typically to update audit trails or related tables. Using truncate when a selective delete is required results in immediate, non-recoverable data loss, destroying everything instead of managing records. Question 2C addresses the challenge of decomposition, splitting a large 8-attribute relation into smaller tables to improve efficiency. For a decomposition to be lossless, the common attribute shared between two tables must be a functional key for at least one. This ensures the data can be reconstructed exactly. In decomposition 1, joining tables R3 and R4 links them by attribute Y. Because Y acts as the key for table R4, the join is mathematically sound without data loss. Since Q determines the remaining attributes, the entire 4-table decomposition is proven lossless. Decomposition 2 is different. Table R2 is completely isolated, sharing no common attributes with the others. Attempting reconstruction forces a Cartesian product, multiplying rows exponentially into spurious tuples, fake records that corrupt the database state, resulting in a lossy decomposition. Verifying intersection keys is the only method to ensure that breaking down a database doesn't inadvertently create false data. Operational stability depends on the 4 ACID properties defined in question 1F. A transaction must be atomic, consistent, isolated from other concurrent tasks, and durable enough to survive a system failure. To maintain isolation, The system locks data hierarchically from database down to record. Locking records allows high concurrency. To manage this efficiently, intention locks are placed on higher levels, signaling a lock further down the tree without needing to search every individual row. Question 2D moves to the final ACID property, durability. We must account for hardware failures, including system crashes and physical disk damage. The DBMS tracks failure in 3 distinct operational categories: logical errors that abort a transaction, system crashes that clear volatile memory, and disk failures destroying non-volatile storage. The system ensures survival through write-ahead logging. Every modification is safely recorded in a stable log before the actual change is applied to the disk. During recovery, the system uses this log to redo committed transactions and undo those that were interrupted, restoring the database to a valid state. ACID properties define transaction safety requirements. The physical architecture of granularity locks and write-ahead logs provides the exact mechanisms to enforce them under concurrent load. The examination solutions demonstrate that a reliable DBMS is built on 2 pillars: mathematical verification of the structure and rigid protocols for the operational state. Functional dependencies ensure the integrity of the data's meaning, while logs and locks ensure that integrity persists through hardware failures and high-traffic access. These solutions provide the specific requirements for building data systems capable of handling both complex relational scaling and unforeseen hardware failure.